Let's get on to the next ordered structure. Start the three dots, the conventional structures, and it's A06. We're loading it, that gets the zip file, it automatically extracts the HKL and ins. What have you got? Nice strong data, good data, nice RND. So hopefully not many problems. Let's see. So first of all, let's just solve it. I'm going to choose structure solution. Let's use shellXT and save a bit of time. And this will solve the structure quite nicely and quite quickly. I don't want the polyhedra now, so I'm going to switch it off. So we have got a metal complex, the same ligand twice by the looks of it, and a whole lot of water molecules. I'm gonna type lines, 3, just so we see something happens, but we don't really want to see what's happening too much right now. And we're gonna refine it and see how the atom type assignment was, the initial atom type assignment. It looks like it was pretty good. So here, I think, well, these are supposed to be the same. This made it an oxygen and this made it a carbon. So let's see what it really turns out to be. Control M might actually tell us here. So oxygen is too heavy and carbon is too light. So switch the Q peaks off, otherwise you might by accident hit a Q peak. Select this and that and make it a nitrogen. And then I suspect that and that must both be oxygens. Right, and then we've got the ligating nitrogen, so that looks all pretty good. Let's put it all together so we got everything as close as possible. Control R for refine and see what we get. All the spheres are about the same size. That's encouraging. Make them anisotropic and automatically refine. That looks very good indeed. Control Q, so there's some Q peaks visible now quite clearly. And I think there might be some interesting things coming up in terms of this hydrogen placement. Just let's see. Let's go for the automatic hydrogen placement. So just H-add and see how well OLX2 does. So it got some quite clearly wrong. So this one here, it put the hydrogen here and not over there. This one, it just needs to be turned around a bit. And those NH2s are quite possibly a bit of a problem. So let's first see what we can do with like a lot of cycles. Refine, I don't know, 30 cycles. Sometimes they just position themselves correctly. So you can see this wants to move, but it doesn't quite make it. It doesn't quite go over there. So one thing we can do is we can help it on the way. So we can effectively go over here and then disorder tools and fit and then just move it. Oops, come on, move it over there. Just where the peak was. I'm not quite sure why I'm so bad at this right now. I didn't select this right, but it doesn't really matter because it's constrained on the parent, so it should just come back together right if I refine this. OLX2 remembers the number of cycles, so if you put in 30 last, it'll be 30 again. Right, so this I think has sorted that one out. So we moved that around. This one here isn't quite sorted. So this one wants to be a little bit further up that way. Let's also this one here. Another thing you can do and try is to delete hydrogens that you've got. And then just try placing H-add again. Just type H-add and it may then get the correct position because OLX2 looks at existing hydrogen bonding interactions and then tries to make the new ones according to what's already there. So often the best way and the quickest way to get your hydrogen bonding network established is to actually delete some of the hydrogens that you're not sure about and keep the ones that you are sure about, and then you usually get there more quickly. The other thing is even try to put it together. So this one doesn't really want to move over there. So we might want to see, are there any interactions between that and that? One way to do this is you can select an atom to which you want to move something else near. So I'm selecting this oxygen and then it's over in view and symmetry generation, symmetry tools, move near. So anything I'm clicking now will be moved as closely as possible to this one that I had initially selected. So if I click there, it moves that over there and that one over there. So we now have all these hydrogen atoms more or less together. So this one we know it's got a hydrogen bond. Let's see whether that moves. It moves out there. So this gives us a nice sort of, establishment of the hydrogen bonds that we do have here. And we can sort of, follow them around. So maybe we can even see whether this one moves and completes that circle. So move near on this one. No, it moves out this way. So this is not a good plan. So let's move it back here. So we have that hydrogen. Oh, that's a better position for it. So now we got that over here. So let's refine it like this. So once you move these things, the refinement will keep them in that place. Control M. So this looks quite good, except for this one here. And I'm not quite sure what's going on here. That water molecule should be okay. So let's see once we fix those NH2s, because they are now the bigger problem here. So you see what happened is it made these NH2s angled as if it was an sp3 type nitrogen, but really it looks like it's more like an sp2 hybridized nitrogen. The distance is 1.365, so this is probably just at the boundary where OLX2 makes that decision. It's a bit hidden. What you need to do is you can go to Tools, and towards the bottom you have this hydrogen atoms thing, and you look at the picture that you like. So this is what we want effectively. It's not really a double bond with two hydrogens, but it's two hydrogens in that system. And if you click on that and then edit like this, it's the 93 affix we want. Now, for some reason, OLX2 puts it in angled, but as soon as you hit, well, first escape to get out of the mode, and now hit Control R, you see it instantly straightens it. I think it's just visually not placed correct, but it actually is the correct constraint you want here. And it's exactly the same here. Delete those two, click on that, and then click on that. And escape to get out of the mode, and Control R. Okay, so that looks pretty good. Control M, let's look at the map. Okay, so this looks like it's a bit of a mixture. It's not really completely flat. It really wants to be over there. One thing you can always do, and I think I'm going to do this with this water molecule as well. It just doesn't turn around. It doesn't seem to want to do that. So that constraint doesn't allow it to do it. You can actually just select those things with Shift and the left mouse and go affix 0. So that removes all the affixes. The hydrogen atoms are now completely free to refine wherever they want to. And if they refine stably to a sensible position, then that's just as well. So now we have Control M, and this is completely clean over here. Not quite sure what's going on here. This is more or less clean. We've got some residuals on here. However, we're not actually quite finished yet, because we haven't actually done the weighting scheme. For some reason, or by sheer luck, the goodness of it comes out right. So we're switching the weighting scheme on, and also make sure we've got an ACTA file. And let's refine this. We don't quite need 30 cycles, but OLX2 refine will stop anywhere when it's done. So it won't go to 30 if it doesn't need them. So that's done a little bit. So the R factor went down. This is a nice line. It looks like there may be a bit of extinction. Let's just try this. But before we do this, let's just refine until the weighting scheme is settled. Control M. Oh, that because there was a big R factor change here. Control M now looks quite clean. So we can clearly see this bonds, electron density on those bonds. We've got something around that vanadium. That's to be expected. There's a big blob here. I'm not quite sure why that's there. So there might be the odd outlier. That's not what I wanted to do. So if that happens, I just put it together. But I wanted to keep the water molecules where they were. File and reload the current structure. You go back to where you were. Your changes are undone. And this thing was something silly that I didn't want to happen. Okay, one question is, why is there no hydrogens on this? And that's because that's a vanadium oxygen double bond. It's 1.6, so that's quite a lot shorter than this one to the water molecule, which will be about 2. Yeah. So that looks quite straight. I don't think there's any extinction here. There's no outliers either, so I'm not quite sure why we're seeing a little bit of residuals that look a little bit smudgy here. However, the level is very, very low. It's only 0.25, so it's not a lot. Okay, so we're nearly done with this, but just to finish this off, you might want to use the htab command. So htab now lists all the hydrogen bonds. So now we haven't got enough lines, so lines -1, so that shows you all the lines. So there's a lot of hydrogen bonding going on in there. And the default htab goes up to 2.8 or 2.9 angstroms distance. So if you want it a little wider, you can go htab 3.1, and this might find a few more hydrogen bonds or bonds that could be hydrogen bonding interactions that weren't there before. So this puts it all into the ins file and also its symmetry equivalents and so on, and then you end up with clean tables for hydrogen bonds in the CIF. I'm going back to line 3, and one thing you can do is htab -g. So this doesn't actually do anything, but it grows the whole structure in such a way that every hydrogen bonding interaction is at least shown once. So many are shown more than once, of course, but every one is at least shown once. So it gets quite messy, obviously. There's a lot of hydrogen bonding going on in that structure. So let's go back down to fuse. I think that's all I want to do in this little Jaca tutorial, and thanks for using Olix 2.